Statistics students, this is the video for section 8.3. There's no actual PowerPoint for this section because it's really nothing new. It's just focusing on the proportion problems. So the good news is section 8.3 is basically just going to be more practice for us. We're also going to only focus now on the p-value method on the hypothesis test. So we're going to not worry about that whole critical value thing. We'll say crit value. So we're not going to focus on that for the rest of this chapter. We will revisit critical value in our last unit of the semester. So we're only going to worry about calculating the p-value, not worrying about the critical value. Okay, so on number one, remember in our 8-step process, the first step is to identify the specific claim and put it into symbolic form. So the specific claim, if we look at the very end here, test the claim that 93% of computers have antivirus programs. I'm going to turn that percentage into a decimal. And remember, this is lowercase p. So p is equals 0.93. It doesn't say more than 93%, less than, it just says 93%. So that's an equals. For step two, remember, essentially it's saying we state the opposite of the original claim. So the opposite of equals 0.93 would be not equal to 0.93. Step three is where we determine our null and alternative hypotheses. The null, the H0, the alternative H1. The statement from the two that I've got so far, again, I've got two statements so far, the one that does not have equality in it becomes my alternative. Clearly not equal to doesn't have equality. So that's going to be my alternative. And remember, for the null, no matter what, it's always going to be an equals. Remember, step 4 and step 5 are very simple. Step 4 is basically to choose a significance level, but I will always give it to you. It is a significance level of 0.01. That's my alpha level. 0 point decimal there, 0.01. Step 5 is to figure out what test statistic I'm going to use. Since we are dealing with proportions, this is automatically going to be a Z test statistic. And let me bring up your green packet. That would be right here. Since we're dealing with a proportion, we know it's going to be a Z test statistic. And that's also the formula we're going to use. So taking it back to the problems. Step 6 is where all the math actually happens. So before I calculate the test statistic, I need to figure out p hat, which is my samples proportion. So going back to the problem, 400 computers, 380 of them had antivirus programs. So 380 out of 400 which if you divide that will give you 0.95. So 95% of them in the sample had that. So again, here's our overarching question. We're wanting to know, is it true that 93% of computers have antivirus programs? Our sample had 95%. Is that so far away from 93 that we can discredit 93? We can reject it. Or is it close enough where we go, we can't really do much? So now that I've got p hat, I can figure out my Z test statistic, which again, this formula is in your packet. P hat, that's a hat, minus P all over square root of P times Q all over N. So p hat Again, I just figured out that's 0.95. Minus P is from my null hypothesis, 0.93. 0.595 minus 0.93 all over square root. And again, be careful here. This is P without a hat on it. That was the 0.93 again. Q would be 1 minus 0.93, which is 0.07. All over N, which was my sample size, which was 400. Again, be careful. Make sure you're typing this in your calculator to make sure it works correctly. If you're going to try to do it all at once, you definitely need to put the numerator in parentheses and make sure in the denominator that everything gets underneath the square root. If you run the numbers correctly, you should round to 1.57. That is my Z test stat. So that's the test statistic. And again, what this is saying, let me bring up a whiteboard here. It's saying if it's true that 0.93 or 93% of computers have antivirus programs, the result we got of 95 is about 1.57 standard deviations away. The question we're asking ourselves is 0.95 far enough away to where we say, oh, this must be the wrong assumption, or null must be wrong? Or is it close enough that we say, yeah, this could happen. Things vary in statistics. That's okay. So since we're only focusing on the p-value, not the critical value, got to figure out how to get the p-value. If we look on our packet for the finding p-values, we need to know what type of test this is. Remember, that goes back to what symbol was used in the alternative. It was a not equal to. That tells me it's a two-tail test. So this is going to be a two-tail test. So this one is two-tailed. The test statistic was positive, so that's right of center. And so the p-value is twice the area to the right of the test statistic. Okay, so I got the test statistic. I need to find the area right of it. And then I have to double that number. So 1.57. I need the area right of it. Remember, your sheet will tell you area left. You have to do 1 minus that. You'll get the area right to be 0.0582. But since it's two-tailed, we have to double that. Oops. And that will give me 0.1164. That is the p-value. So it's basically saying the chances of getting 95% if 93% is correct, or sorry, getting an answer at least as far away as 95%, not just 95% itself, but at least as far away as 95%, has about an 11.64% chance of happening. Yeah, that's not a huge percent chance, but it's not very weird. And to make it official, do we reject or fail to reject? That is when we look at the p-value, which was, again, 0.1164. And we look at it in comparison to alpha, or significance, 0.01. So on this problem, we basically said, if something happens 1% or has a probability of happening of 1% or less, then it's weird. Well, ours was definitely not. Our p-value was definitely bigger than our alpha. So that is a fail to reject. Weird things aren't happening. And again, it's always the null. So we don't have weird enough numbers to where we can say, oh, our original assumption must have been wrong. And finally, to state the final conclusion, that's where we go through this other flow chart. So did the original claim contain the condition of equality? Yes, it did, because it was just said that 93%. There we go. So yes, it did, but we failed to reject it. So this is how we'll word our conclusion. There is not sufficient evidence to warrant rejection. I'm going to do this in shorthand. The nicely written answers are in the answer key that's posted on Blackboard. So basically, not sufficient evidence to reject. Sorry, not sufficient evidence to reject the claim that 93% of computers have antivirus programs. So what we basically came up with is, we don't have enough info. Yeah, 93% is different than 95, but they're not so different that we can say 93% is wrong. I'll do the next problem on the next video.